Okay, so let's get started. Good of you. Do you know how to hide it? Just leave it like that. Okay. So we'll just get started with Edward's going to be telling us about Fox-cartesian structure for Gray-Monoidal double categories.
Okay, thank you. Indeed, I am Ed, and I'm going to tell you about Fox-cartesian structure for Gray-Monoidal double categories. I'm going to start with a one-slide overview to give you an idea of what to expect in the next half hour. In the 1970s, John Gray defined this monoidal product functor for two categories that's left adjoint to the internal Hom, and he used it to give an algebraic presentation of the three-dimensional structure formed by two categories together with their hierarchy of their morphisms, so that's to say the functors, transformations, and modifications. A lot more recently, Gabriele Böhm defined a Gray-Monoidal product functor for double categories, and she used this to define Gray-Monoidal structure for them as well. Flashing back to the 70s again, Tom Fox characterized the Cartesian structure on symmetric monoidal one-dimensional categories in terms of a natural duplication, deletion, comonoid structure, which we heard about yesterday in Elena's plenary talk. So what we're going to do here is adapt this Fox-cartesian structure to the setting of Gray-Monoidal double categories. Okay, sorry. I'll talk and hopefully you can see soon. And we'll describe the theory of this thing in the graphical language of surface diagrams.
Options at the top. Hide video panel.
Second one, this one.
Immersive?
Immersive, maybe? Oh,
okay, never mind.
If anyone knows what to do, let me know. But I don't.
Dot at the bottom right.
I thought it was bottom right, but I couldn't see anything obvious.
Yeah, you can't do that.
If you hit Alt, it should work. Try hitting Alt.
Alt? Alt.
Okay, okay, great. Okay. So in order to tell this story, I need some ingredients, and that's what I'm going to introduce now. In particular, we're going to need some structures from the theory of double categories. We're going to need double categories themselves, the pre-unitary weak variety, if that means anything to you. We're going to need functors for double categories, in particular strict and doubly-lax ones. We're going to need transformations for such functors, both horizontal and vertical. And finally, we're going to need cubical modifications for these functors, transformations, sorry. So you may know about these structures already, possibly from Duret's tutorial yesterday, but I'm going to briefly describe sort of another way of thinking about them that's going to serve my purposes. So we can understand these things in terms of a structure that I call a locally cubical Gray category. And this is a three-dimensional categorical structure that's cubical in two of its dimensions and globular in the third. So let me describe this to you. I'll start with the cell structure. We have a collection of 0 cells. And for each ordered pair of 0 cells, we have a collection of 1 cells with that boundary. And then if we have a parallel pair of 1 cells, that is with the same 0 cell boundary, that determines a collection of vertical 2 cells and also a collection of horizontal 2 cells. And finally, if we have a pair of vertical and a pair of horizontal 2 cells with the appropriate collection of 1 cells, all bounded by the same pair of 0 cells. I think I misspoke. We want 4 1 cells, but anyway, it determines these this collection of 3 cells. So I've been drawing these things over here on the right in surface diagrams, and what's going on here is that the local structure of a locally cubical Gray category is indeed just that of a double category. So here, this configuration of cells is the one that describes the middle four exchange, which we learned about yesterday in the tutorial. And this, we can represent these things by drawing them as string diagrams embedded on surfaces. So if you're not familiar with this string diagrammatic representation of double categories, David Jasmyers has a really nice article describing this that I refer you to. Okay, and also to orient you, I'm going to draw these diagrams left to right, top to bottom, and front to back, so you read them just the way you read a book. Okay, so now I've told you about what's going on locally. I need to tell you about what's going on in this new dimension, this principal dimension, or transverse dimension, as I will sometimes refer to it. So there, if we have natural numbers m and n, whose sum is bounded by 2, we can compose an m+1 cell, with an n+1 cell to obtain an m+n+1 cell, so long as the 0 cell boundaries are consecutive, in the sense that the codomain of the first is the domain of the second, in which case the composite has the transitive boundary, as you would expect. And the nice thing about this is that we can just read off the boundaries of composite cells by looking at the projection string diagrams of surface diagrams. So if either m or n is 0, this principal composition goes by the name of whiskering. I'll write this with this infix circled asterisk operator. And here on the left, we see this surface diagram where we have a 3-cell phi, whiskered on the left by this 1-cell A. And if we want to know the boundaries of this composite, which will be a 3-cell, we can take this surface diagram and just project it in this transverse dimension, which is to say, sort of just look at this surface diagram from left to right. And then the string diagram we would see is depicted here on the right, along with all of the lower dimensional boundary data. So we can whisker on the left, like we have here. We can also whisker on the right. The shape of the composite remains the same, but the labels change. But we can obtain a 3-cell not only by whiskering a 3-cell by a 1-cell, but by the arithmetic of dimension composition that I mentioned earlier. We can do it by composing 2 cells. So that goes by the name of interchanger, and I'll write this with this chi. And so here, this surface diagram depicts the interchange of this vertical 2-cell alpha with this horizontal 2-cell delta. And again, if we take the projection string diagram of this surface diagram, we'll see this picture over here on the right. And we could have put the 3-cell here with a dot and a label, as we have been doing, but it's more convenient to draw these using this crossing notation, because these interchangers are the canonical or the structural cells determined by their boundaries. So once we know what the boundary is, we can know what cell we're looking at here. Of course, we can interchange a horizontal and a vertical 2-cell in the opposite order, and we just get the other kind of crossing here. But we can also interchange 2 cells in the same dimension, which is to say 2 vertical 2 cells like this, and this gives us this interchanger, or 2 horizontal ones, and that gives us this interchanger. And this variance or orientation of the homogeneous interchangers is known as the op-lax orientation. Its opposite is known as the lax. And if we have invertible interchangers, then that's called pseudo. And if you want a nice mnemonic for this, in an op-lax interchanger, the latter 2-cell is eager with respect to its predecessors in the composition order here, and therefore lax one is lazy, and I guess that's the mnemonic, right? Lax and lazy being synonyms.
To what extent you...
You can have either or both. It's parametric in the variance of the interchangers. Okay. So now we know how to make composite cells in this new dimension. Let's talk about the laws of composing them. So first, this principal composition is strictly unital and associative with respect to the, and it's compatible with a local composition structure in the Hom double categories. Okay, so the nice thing about this, as long as the dimensions are not too high, that is the m plus n doesn't exceed 2, we can just read off the laws of composition from surface diagrams. So I'm going to give you a few examples of this. Here is a surface diagram depicting two vertical 2 cells with this intervening 1 cell. And we can interpret this diagram in a couple ways. We can either take alpha here and whisker it by b on the right, take the resulting 2 cell and interchange it with gamma, that's this expression here. Or we could sort of right associate this diagram, and we can interchange alpha with the result of whiskering gamma on the left with b, that's this right expression. And well, the law says that these expressions represent the same cell, as we would expect, because I said that these that we have strict associativity in this principal composition dimension. Here's another example. We have two 3 cells that are horizontally consecutive, phi and psi, and we could compose up this diagram either by first composing phi and psi horizontally and then whiskering the result by b, or we could whisker phi and psi by b each individually and then horizontally compose the result, and that's the 2 sides of this equation, which again are identified. Finally, here's one that's maybe a little more tricky. We have these 3 vertical 2 cells, 2 of which are consecutive, and we could either interchange alpha with a composite of beta and beta prime, that's this expression here on the left, or we could break this down into smaller steps. We could interchange alpha and beta, compose that vertically with the result of whiskering beta prime by f prime on the left, and then take the resulting cell, compose it horizontally with the result of whiskering beta by f, and then taking the identity cell on that, composing that vertically with the interchanger of alpha and beta prime, and that's this intimidating looking expression on the right. But the point I want to make here is that even though when we try to linearize these things, they can look kind of ugly and disorienting, the point is that they're just different ways of describing the same sort of geometric situation. Okay, so what happens when we bust our dimensional budget in the sense that our m plus n exceeds 2? So if we look at this diagram, we have this vertical 2 cell and this 3 cell, and we can't compose these to get structure because according to our dimensional arithmetic, this would result in a 4 cell, and there are no 4 cells in this 3-dimensional theory. So what do? Well, we do the same thing we always do in category theory. When we run out of dimensions to define structure, we punt and we define properties instead. So what we can do is we can take this diagram and perturb it slightly to move this phi either up and to the right, the psi, and move it up and to the right away from the alpha, or down and to the left. And the resulting projection string diagrams that we get are the following. And the law says that these are equal. Well, almost. So notice I've written this as equivalence, not equality. And the reason is, in the introductory slide, I mentioned that we're dealing with what are called pre-unitary weak double categories. And if you notice that the vertical boundaries here aren't exactly equal, they're off by uniters. So we have to conjugate these diagrams by uniters to make them equal. But that's not conceptually very important. Good. So why did I just spend 10 minutes telling you about locally cubical gray categories? Well, there's a couple reasons, but one of which is that this is the structure formed by double categories themselves. So if we take double categories to be 0 cells, strict functors of double categories to be 1 cells, vertical transformations and horizontal transformations, each independently of whatever variance we want, to be the vertical and horizontal 2 cells, and the cubical modifications to be the 3 cells, then we get one of these guys. So even if you were a little fuzzy about what these things mean, now you kind of know, because you can work out the laws from what I just sketched for you. And as a sort of sanity check to make sure we're on the right track here, if we specialize this definition to the case where we have only identity horizontal 2 cells, we recover something that's equivalent to the classical, that is to say the locally globular notion of gray category. So this should give us some confidence that we haven't done something completely nuts in this definition. Okay, so now I've defined the structures I need in order to define the structures that I want. Let me define the structures that I want. So I want to start with a symmetric Gray-Monoidal double categories. Let's table this symmetric for just a moment and talk about Gray-Monoidal double categories. And in general, whenever we have an X-monoidal Y category, there are usually two equivalent ways to think about this. One is we can think about it as a one-object Z category, where a Z category has one dimension more of structure than a Y category. Alternatively, we can think about this as an ordinary Y category with some additional structure to give the X-monoidalness of it. And the setting here is no different. So one particularly concise way to define Gray-Monoidal double category is to say that it's the loop space of a one-object locally cubical Gray category. So that's concise, but may or may not be enlightening. If we unravel this definition, we discover we get back essentially what Gabriele Böhm got in the work I mentioned in the introduction. And she did this, I'll remind you, by using this, this Gray-Monoidal product functor for double categories. So if we take this functor and we look at its zero-dimensional component, that is its action on double categories themselves, we can define this thing which I'll write like a tensor, so like C tensor D for double categories C and D, and I'll pronounce this thing as the Gray ordered pair double category. And there, an M plus N cell of such a double category consists of an ordered pair of an M cell from C together with an N cell from D. So because we're in the loop space, if you remember the arithmetic of dimensional composition that I mentioned earlier, all those plus ones go away and the dimensions add the way you would expect. So if you want a slogan for this part of the talk, it would be that Cartesian monoidal structure is dimension souping, while Gray-Monoidal structure is dimension summing. And if we have a double category, C, then we can define Gray-Monoidal structure on it if we have functors that sort of internalize this Gray-ordered pair construction of C with itself into C, and then another functor that picks out an element of C, and these two functors together form a monoid. So that gives us a Gray-Monoidal structure on a particular double category. Okay, so now let's try to get up to the symmetric stuff. So in order to do that, we need braiding. In order to get braiding, we need a swap functor. So a swap functor just takes a Gray-ordered pair double category and reverses the factors. So here it turns this cell into this cell, turns this cell into this cell, and so on. So you should notice that it's doing something to the interchangers. For example, here it's turning this op-lax interchanger into a lax one. Okay, so if we have a Gray-Monoidal double category with invertible interchangers, I'm going to come back to this invertible interchangers in just a moment because it's going to be important, but I want to finish this definition. We can define a braiding for it as a vertical pseudo-transformation from the tensor to the tensor following the swap. So here I've drawn an arrow component square for such a thing, and it has the boundaries shown here. And this thing has to be coherent, and this was all worked out previously in the globular case. It has to be coherent with respect to the monoidal composition. For the binary composition, this was worked out by Kapranov and Vygotsky, and for the nullary composition by Kranz. And for us, this is basically going to mean if we have a surface diagram like this and we paint like string diagrams onto the surfaces, then they have well-defined interpretations. It also has to be coherent with respect to the Yang-Baxter-iterers. The Yang-Baxter-iterers are categorifications of the Yang-Baxter equations, which relate the two ways of reversing the order of three things using three braidings. So here I've tried to draw such a thing, and with the boundary shown here. And the coherence has two parts. First, it turns out that there's two ways to define such a thing using the generators that we have at hand. And so one of the coherences identifies those two. And the second coherence is this. I'll explain this only very briefly. Basically, there are 8 ways to reverse the order of 4 things using 6 braidings. any two of which are related by Yang backstreiters, but they're related in two different ways, and this coherence identifies those two ways. Okay, so let's come back to this question of why we need invertible interchangers. So let's look at this diagram here, where we have an interchanger of prairies M and N, and we have this braiding. So this diagram can't represent a piece of structure because the dimension is too high, right? This interchanger would be a 2-cell, and this braiding is like a 1-cell, and so where they intersect here, this would be a 3-cell, but we're in a braided Gray-Monoidal double category, so there's no 3 cells. So this must represent a property. What property does it represent? Well, we just take this diagram and we perturb it slightly to remove the forbidden 3-cell, and these are the two diagrams that it relates. So basically what we do is we take this interchanger and we nudge it either slightly up or slightly down. And the point I want to make here is that depending on which of those things we do, we're going to get, in this case, an op-lax interchanger if we move it up, and a lax interchanger if we move it down. And so if we didn't have invertible interchangers, one of those two expressions might not even be defined. So in order for this to be well behaved, we're going to want invertible interchangers. Okay, so we can categorify not only the Yang-Baxter equation to a Yang-Baxterator, but the symmetry equation, and that categorification goes by the name syllepsis. It relates the unbraiding, or no braidings of two things, to two consecutive braidings. And here I've drawn an object component square of such an invertible globular modification with the boundaries shown here. And again, this was worked out in the globular setting previously, in this case by Day and Street, who have a coherence that say this has to be compatible with a monoidal composition, like this. And it needs to also be compatible with the Yang-Baxterators. So what's going on here is that we have this A and B, which are sort of parallel, and we can introduce a syllepsis here. We can use Yang-Baxterators to get this double crossing across the braiding with C to move it down here. And then we can remove it with the inverse Yang-Baxterator, and these things are identified. So maybe this is a good point to just pause and say, like, what's the idea here? Like, how are we coming up with these coherences? Well, in this setting that I'm working on, which can be described interchangeably as geometric or monadic or unbiased category theory, the inside game is basically if you have some kind of diagram that can be decomposed in multiple ways, that is, that can be explained by multiple expressions, you want to identify those expressions. And then when you reach the highest dimension, if there is a highest dimension, if you have multiple things that you can build out of the generators that have the same boundary, well, then you punt and you identify them with a relation. So that's kind of the guiding principle behind all of these coherences, which may seem difficult to motivate. Okay, and finally, syllepsis is called a symmetry if it forms the unit of an adjoint equivalence. So here you can see the syllepsis sitting right there, acting as the unit. The co-unit is the inverse of the syllepsis with the factors in the other order. And of course, in an adjoint equivalence, we have one of the adjunction equations, just in case we have the other. Good. So now, finally, to the Fox-cartesian structure in the title of the talk. If you remember back to the slogan I gave you a few minutes ago, you might think that, well, we can't actually have some kind of a duplication structure for these things, these Gray-Monoidal things, because that would bust our dimension budget, right? Remember, the slogan was that Gray-Monoidal structure is dimension summing. But it turns out that we actually can duplicate things. We can have two copies of something. We just can't have them at once. We have to impose an order on them. So we need a map that can make two copies of something, but we have to pick an order. We can't have the two copies at the same time. So here's a map that takes this square alpha and gives us two copies of alpha in a particular order. Here's another map that gives us two copies of alpha in a different order. And indeed, there's two more orders that I haven't drawn here that you can think about. But once we have this, we can try to use it to define duplication structure. But the first wrinkle we encounter is that this map can't be a strict functor of double categories because it doesn't strictly preserve the composition. So in order to see this, let's look at this diagram here on the left. On the left boundary, we have 2 copies of F followed by 2 copies of G. On the right boundary, we have 2 copies of F followed by G. Now, these 2 boundaries are clearly related, but they're not identical. And what relates them is an interchanger, in this case, doubly-lax interchanger of F and G, which act to collate the copies, put them in the right order. And we need to be able to do this in both dimensions. So we're going to have this like laxness structure with the comparators that do this collation in both dimensions. Okay, good. So once we have this, we can define a duplicator doubly-lax transformation of unitary pseudo-functors. Oh my gosh, okay, that's a lot of adjectives, so let me demystify them briefly. First of all, this unitary says that we don't need to do any collation with nullary composition because there's nothing to collate. This pseudo-functor tells us that we have invertible interchangers, which I mentioned before, why we need these. And finally, this thing is, where'd my pointer go? Oh, all right. Okay, I don't know what happened there. But anyway, this thing has to be doubly-lax so that we can duplicate arrows rather than unduplicate them. It's not super important to understand this, but I just want to explain why it's the way it is. But the nice thing is that because these things are transformations, we automatically get naturality for squares, which says that if we have a square and we duplicate its codomain in either dimension, then that's the same thing as duplicating the domain and then having 2 squares sort of all in the right order. Once we have this transformation, this duplicator transformation, then we need a modification to act as a coassociator. This does exactly what you would expect. I've tried to draw on an object component square of such a thing here with a boundary shown. It's just a structure categorifying the coassociator. And we also need to do the same thing with the cocommuter. This one's a little bit more interesting because if you look here, the duplicator we use on the 2 boundaries here are different. They're the opposite duplicators that I introduced a few moments ago. And the reason for this is because in order to be a modification, we need to be natural with respect to arrows and pro-arrows. And to do that, we need to preserve the boundary structure as we pass across the component here. So if you work out what would happen on the boundary, if we didn't change to the other order here, right? Like we have some order on the left, and if we use the same order here, then when we do this braiding, it's going to mess up the order, and we're going to get a different order. So we need to use 2 different duplicators on the boundary in order for this thing to be a well-behaved modification. Okay, and then there's some coherences, some coherence porn I'm not going to spend too much time on, but just notice that you can go from the first to the last of these in one step by using the black coassociator, and we can do this like clever other way by using the white coassociator backwards, using some commuters and braidings to get things into the right position, and we just identify these by the desideratum of coherence that I mentioned earlier. Finally, we need this deletion structure, so I have to find the object component arrow, pro-arrow component square, and arrow component disk for those here. The naturality for squares for that says that if we have a square and we delete its codomain, then that's the same thing as deleting the domain and forgetting about the square. We need modifications to act as co-unitors, and they have to be coherent. So what I am proposing here is that we tentatively define a symmetric Gray-Monoidal double category with this duplication and deletion structure as Fox-cartesian. So why does it sound like I'm hedging here? I would like to actually just delete the text in the parentheses, but there is some reason for caution. So if you know anything about the history of this kind of thing, like trying to give algebraic presentations for categorifications of structures, you'll know it's notoriously easy to make mistakes in the coherences, insofar as either leaving out important coherences that you need or discovering that some of the coherences you've defined are redundant. And I'm not confident that I've avoided either of those mistakes. So I think that there's still sort of some investigation to do here. And what I would really like is, of course, to have a universal construction characterization to compare the algebraic characterization to make sure we're on the right track. Anyway, I'm out of time. If you're interested in this, you can have a look at this preprint on the archive, and I thank you for your attention. Here's the articles that I referenced during my talk.
Thank you, Ed, for an interesting talk. Any other questions? Yeah? Oh, well, I can try speaking to that. It should work.
So, sorry, say again?
Can you tell us an example of a Gray-Monoidal double category or one with a Fox-cartesian structure?
Without?
An example. Tell us an example of one of the things that appeared in this talk. Thanks.
Well, I haven't really thought much about examples, so I'm still just thinking of definitions at this point.
Did I see that Oxford CS raised a hand online? No?
Yes. I have a question. Thanks for thanks for the great talk, Ed. My question is, these like string diagrams or these surface diagrams you've drawn, can they give the semantics for other surface diagrams in the literature? Like, for example, like these like proof services for ring categories, because like a ring category is like a categorified Levier theory. You thought about like the connections to other proof service kind of string diagrams?
Not exactly sure I understand the question, but you're saying like for other theories that can be represented
like in the literature, like other like kind of string diagrams that use like proof services, like, or did these give semantics for them? Anything in the literature?
I have not given semantics for other theories in the literature, no.
Okay, thanks.
Guess we've got time for one more question. There's one. Bryce?
So this is sort of just a technical question. I mean, usually there's two kinds or two flavors of Gray-Monoidal product. You have the lax one and the pseudo one. Which one are you working with here?
So this is parametric, right? It goes back to, you can define whichever variance of interchanger you want.
Okay.
Here, right? So you can pick lax, op-lax, and or, right? And if you pick both, then you can have pseudo. So you can have whichever you want. You just have to be consistent in each dimension independently. But you can mix and match as you like. So it's a parameter to the definition.
Okay, let's thank Ed again, and we'll go for coffee.